exercise 1, and this is on the precise definition of a vector function limit. And we're asked to show that the limit t, as t approaches a of the vector function r of t is equal to b, the b vector, if and only if for every, these are Greek letters, epsilon greater than 0, there is a number, delta, greater than 0, such that if we have this interval where t minus a, the absolute value of it, is greater than 0 and less than delta, then this interval right here, the vector function r minus the vector b, the difference is less than epsilon. So basically what it's saying is that we can make this as small as we want as long as it's positive, and then this will always have this scenario. We will always have a t value, a t value that's basically if you make this really small, you can make this this interval also really small, but again positive, but not exactly 0, but all you can make it almost equal to 0, and this basically this interval gets smaller and smaller, t minus a, and then you'll always have a scenario where this r of t minus b vector, they're always going to get smaller and smaller. Basically, the difference between the two goes to 0. So in other words, if the difference is going to 0, the limits are equal. So they are approaching each other in value. And here, just to illustrate that, we'll do a quick recap before we go over to the solution. So recap on limits. So recall the precise definition of a real valued function from my earlier video. So here's the definition. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write limit as x approaches a of f of x equals to L if for every number epsilon is greater than 0, there is a number delta greater than 0, such that if we have the difference right here, the interval x, the difference or interval x minus a, the absolute value is between 0 and delta, then the difference between the function and the limit is going to be less than epsilon. So, and this is when we can make this this is for every positive number epsilon. So we can make this infinitely small, and then this will still be satisfied because this gets infinitely closer to this. In other words, the x value, we will always have an x value that we plug this in. This becomes infinitely small, and this gets infinitely small. And in other words, these are all approaching each other, or this one's approaching the limit. So, and we'll illustrate that right here. So here's an illustration of that. So what we have, I'll just zoom in right here. So if we have right here, this is at a. So let's say this is our number right there. Yeah, so this is at a, and then there's the limit L, like that. And basically what these intervals mean, so now if we have this interval epsilon right here, and this is our function f of x. Yeah, so this is y equals f of x. This is, I used the AI upscaler, I kind of messed up that equal sign. This one wasn't that good of a quality image. But anyways, what happens here is, yeah, so this interval right here, this is f of x minus L. So if we have L right here plus epsilon, and then so this is the interval right here. This is basically f of x, or actually this would be right here, f of x minus L, like that. This is going to be less than epsilon. All right, so it's between that, but then it's and then if you have it also on the negative side, so you can also have it over here, this interval, and this is because the f of x could be higher, it could be lower, etc. You could have it over here, you could have it over here. So then this difference is going to be epsilon right there. And as we get closer and closer to a, if the limit exists, then basically all that ends up happening is, so that's the a value. We'll go over here now. So we know f of x is in here. And now if we shrink the interval, this is the delta now. So before it's epsilon, the delta is dealing with this x variable right here. So when x is in here, and x is not equal to a, just approaching it. So as you're approaching it right here, you're always going to have a scenario. Yeah, you're always going to have a scenario where f of x is always going to be within here, like that. And in this case, right here, we're using this one as the maximum one, and then hence why it's over there. But then if we go and shrink it even more, what ends up happening is, well, we shrink it all the way even smaller. So then what ends up happening is the intervals becomes even smaller there. So now this is the epsilon. So as we shrink it, and then eventually you basically get all the way to this point. So in other words, we can get smaller and smaller, and there will always be this epsilon value. and in a corresponding delta value. That just all they do is get smaller and smaller until we get to like all the way up to here and here. So the interval is going to be there. In other words, it's approaching that value. All right. So I just want to recap on that. Also, for my own sake, it's been a while since I covered that in a precise definition of limits. So now let's take a look at solution 1. So now we're going to do this for vector functions, and instead of dealing with limit L, a real number, we're doing this is the limit B is going to be a vector, and instead of this is a function, this is a vector function, and so on. And this one here, instead of x minus a, we have t minus a, where t is a parameter. All right. So solution 1, let R of t be a vector defined on some open interval containing t equals a, except possibly at a itself. All right, and let B be a vector in R3, in other words, basically in 3D right here. So let's write this out, and also, yeah, basically so let's write these down. So R of t is equal to, so basically it's defined on an open interval, the open interval is basically just the endpoints. It doesn't need to equal or it goes infinity, etc. So we have it like this. This is going to be containing, and this is going to be, we're just going to write these in component parts. I'm going to write this as, so let R of t vector function equals to the component parts f of t, g of t, and h of t, like that. And we let b, so we let that, and b, the b vector of t is equal to, this is going to be, this is, this is just a vector, it's not b of t, this is just a straight vector b, like that. So this is equal to, we'll have real values b1, b2, b3, like that. All right, so in this solution, what we'll do is, I'm going to write if, so if we have, if the limit right here, as t approaches, so we're just going to assume it's true. So if the limit as t approaches a of the vector function R of t is equal to b of t, then what this means is the limit exists. Then limit, let's write that here. So if it's equal to that, then the limit has to exist. And this is going to be limit R of t exists. And if the limit exists, then, well, thus, by definition 1, we're going to have, and if we recall definition 1, I'll just jump over to, so here I just jumped over here. So this definition 1 is going to, so if limit exists right here, or I mean, if you have a vector function right here, R of t equals f of t has components f of t, g of t, h of t, then if the limit exists, then this is by definition, the limit of this vector function is equal to the limit of its components, the limit of f of t as t approaches a, and so on. This limit of g of t, limit of h of t. All right, so that's by definition 1. I'll just teleport it over here. So limit as t approaches a of R of t, this equals to the limit as t approaches a of, this is going to be f of t, limit as t approaches a of, this is going to be g of t, and limit as t approaches a of h of t, like that. Alright, so now we have this by definition, but we also know that, well, we're told right here, so we're starting off if this equals to b, so if these vectors are equal to each other, so well, by definition of just basic equal vectors, this has to equal to, this is b1. This is because it's equal to the b vector, so this has to be equal to b1, b2, b3, like that. So what I'm going to do is, so then they're equal to it, thus we're going to have 3, so then these ones have to be equal to them. Now we have 3 different limits that don't have the vector function anymore. So we are going to have limit as t approaches a of f of t is equal to b1, and I'll write this down over here now, limit as t approaches a of g of t, this equals to b2, and finally limit as t approaches a of h of t equals to b3. All right, but right here, these are these are limits of real valued functions. So by the definition of limits, for every epsilon greater than 0, there exists delta 1 greater than 0, delta 2 greater than 0, and delta 3 greater than 0. Since 3 greater than 0, such that, so we're going to have such that if let's put this right here. So now we have the interval right here. This is, again, this is going back to the limits. Recap on the same thing here. So these are just real functions. So now this is where we're going to have epsilon and delta. But instead of writing epsilon 1, 2, 3, I'm just going to go epsilon divided by 3. That's my solutions manual laws. So we're just going to have write this right here, interval x minus a between 0 and delta. And now we'll have this. Then we're going to have f of x is going to be less than L. And this is between here. Now, yeah, less than L, I mean, the difference is going to be less than delta. In our case, we're going to just divide it by 3, and I'll illustrate why. So we're going to go right here. This is t minus a. This is delta 1, then. And in our case, then we're going to have now the difference between f. Now, this is for here, f of t. Minus, the limit is b1 now. These are just regular numbers there. And this is going to be less than, and we're going to write this as epsilon divided by 3, just because we need to equate these to the real value function limit. And here there's 3 components, so we're just going to divide these all out in thirds. But again, remember, epsilon could be any number, so it doesn't really matter too much. It just gets smaller and smaller. But here we're just going to divide it by 3, just because we have 3 components, and so it'll be a bit more accurate. If we were to graph these all out, if we actually get real values for them. Anyway, the second one is going to be, again, t minus a less than delta 2. Then g of t less than b2. And that's just this one right here. That's going to be for every number epsilon, epsilon divided by 3. Less than epsilon divided by 3. And I'm going to write this a bit better. Now the next one is if. Alright, so if 0 less than t minus a, and then less than delta 3, then we're going to have h of t minus b3 less than epsilon divided by 3. Alright, so just divide that out. So we could have done epsilon 1, 2, 3, but we'll just divide it by 3 in this case. And it's the same thing. These are still epsilon 1, epsilon 2, epsilon 3, but they're all just equal to each other. All right, and so now what we'll do is we'll put these all together. Again, you'll realize why we had this divided by 3. So basically, we're going to sum all these up because we want the full summation right here. Because we want to deal with the vector function right here as opposed to just the components. So so these are the individual components as limits. So now if we let delta without a subscript equal to the minimum of the delta 1, 2, and 3. This is going to be 3. Yeah, so we'll take the minimum of it. So that again, these could be any numbers, but we'll just deal with the minimum. And so and if it's the minimum, then that fits every requirement. So for example, if this is the minimum, then this will still be less than S1. Delta 1, delta 3. So these will all fit. So we'll take the minimum of it. Then if we have 0 t minus a, and then this is the absolute value of t minus a is less than delta, then we're going to have, now if we sum all these up, so we're going to sum all these up, f of t, and then plus g of t, this f of t minus b1 absolute value, plus this one, we're going to get is a minus b1 plus g of t minus b2 plus, this is h of t minus b3. This is going to be equal to, well, actually it's going to be less than e3 divided by, epsilon over 3 plus epsilon over 3. So just sum all those up, and this is equals to epsilon. All right, so now we have this, and we'll tie this all together, but because we know that, well, but if we look right here, if you recall, so this one here, we're just assuming that it's true at the beginning. So if we have this right here, actually going back into the definition side right here, yeah, so basically the limit will right here of the vector function r of t as t approaches a will equal to the vector b. So if we have this scenario for the precise definition, we need to show this. But first, what we'll show is that if we take, we're going to have this scenario, we'll have the vector function minus the b vector, and that's going to be less than the epsilon. So we always have this case as we make this smaller and smaller. Hence, that's how you can show that the limit exists. So now this one right here, the magnitude or the difference between here, this is just the length of these difference of these vectors. In other words, this one is just using the Pythagorean theorem in 3-dimension, or just the distance formula in 3D. So we'll go over this right here, and I'll recap that later. So, but the difference right here, so I'll just write this as but r of t, the difference, the magnitude right here of the vector function r of t minus b vector, this equals 2. So, well, first of all, this equals 2. This is the difference right here. Before I get to that, this equals 2 in its component format. This is just equal to. Let's put the full length outside of it. In vector form, these are just subtract the 2. So, in other words, this is just f of t minus b1, like that. And then the middle component is g of t minus b2. And then the next one is h of t minus b3. And then we want a length of that, and then this all equals 2. This will just equal to the square root of, again, the absolute value of it is going to be the distance. This is going to be f of t minus b1. I'll put it like this. Squared plus, and this is just, again, this is distance between difference of vectors there. This is just distance between those 2 points. Essentially, this is going to be now g of t minus b2 squared plus h of t, I'll put the square bracket, h of t minus b3 squared, like that. Alright, so we have this, and what we also can do is, well, this is going to be less than or equal to, and it's going to be less than or equal to by, well, if we take these all together and basically look at these each separately. So instead of adding all these up, what we're going to do is just add up this one right here, take the square root plus this one plus that, and then it's going to be less than or equal to it. Yeah, so this one right here is going to be less than or equal to, and we're just doing basically the maximum size we can do. So what I mean by that is it's the same thing as writing right here. This is square root f of t, b1 like this, squared. So we square root this, like this, and then plus. So then this is going to be a positive value, squared plus this one. So then this difference is going to be, well, less than or equal to this one. This is, you're not going to get anything bigger than this one. This is going to be g of t minus b of t squared plus last one h of t minus b of 3 squared, like that. Alright, and then going further, this equals to, well, then I'll just separate these. Yeah, cancel the square roots and the squared. So then this is going to be right here. Put this, take the absolute value sign in this, because this is also positive there. So this is going to be absolute value sign f of t minus b1 plus absolute value of g of t, the difference, minus b2 plus h of t minus b3, like that. So that is what we have there. So in other words, this difference is equal to the summation of these differences. In other words, this right here, we already have these. We already solved this one right here. This is just from the component parts, and this is going to be less than epsilon. So this is we just solved the thingy. So less than epsilon. So if the limit exists, the difference needs to be less than epsilon. And again, that's if this, and this is where t minus a, the absolute value of t minus a is going to be between 0 and epsilon. So in other words, we literally just solved it. Yeah, so in other words, yeah, we solved this. So thus, for every epsilon greater than 0, there exists a delta greater than 0, such that we have, such that 0 less than, this is going to be t minus a delta. Or I'll actually put the if sign. So if there. So if 0 is t minus a, the absolute value of that is going to be between greater than 0, less than epsilon. Then what we have is, well, this is the difference between the vector function and the vector b is less than epsilon. I mean less than less than right here. Yeah, so thus we have this, and then thus our initial one is true. Well, we assumed it was the vector existed, and now we prove that it does by the precise definition. So thus we'll just go back to here, limit as t approaches a. I just put this for completeness in one section. This right here exists, equals to b vector. Yes, we just solve that. I'm going to solve it a different way. And here I quickly just, actually before we get to the second solution, I'll just quickly change things up. So basically I wrote this here. So this proves our limit, and I'll just put the limit right here. Limit as t approaches a of the vector function r of t. This equals to b vector. Yes, so now let's continue further. And also one final note. Note that I used the distance formula in 3D for my earlier video, and that's for here, right here. So distance between, this is just basically the magnitude is just, or difference is the same as the distance between these two vectors. This is a vector function and then vector b. And I just used that for my earlier video as a link to it, and there's the thumbnail of it. And basically the distance between p1 to p2, you could same thing as writing it as if they're vectors, you could do the vector between them. But anyways, the magnitude or the distance is going to be equal to the square root of the difference of each component squared. So x2 squared, x2 minus x1 squared, and then so x2 minus x1, y2 minus y1, and then z2 minus z1 on all those squared, and then square root the whole thing. Right, so epic stuff. So now let's take a look at the solution to this again, but in a different format. Just the solutions manual had two different solutions, so we'll solve it using a slightly different method. And the first one we started off with assuming that the limit existed, and then showing that this is the case. But now we're going to go the reverse. We're going to start from here and then going all the way back up the other direction. So conversely, suppose for every epsilon greater than 0, there exists delta greater than 0, such that if, all right, we'll write if, and then we'll do the usual. So the interval, this is t minus a. The absolute value is between 0 and epsilon. So we're going to have, now the difference is going to be here. So suppose we have this scenario, and then we're going to go back and prove that it's actually the limit. This is the rt. This is the vector function minus the b. This is going to be less than epsilon, like that. All right, so now we have that. So then we'll go from here now. So thus, put that over here. Thus, this is going to be now rt. Just take the difference from here. So now we're doing from this direction as opposed to, again, from solution 1 was the reverse direction. So minus b, put these in components. This equals to the same thing as difference. This is going to be f of t minus b1. All right, so it's b1, and g of t minus b2, and then h of t minus b3, and then absolute value sign. All right, and also, this is going to be less than epsilon, so move it over, less than epsilon. All right, so we have this now, and now what we'll do is again apply the distance formula right here. So then do that over here with this. So then this is going to be the magnitude is equal to, put it like this, square root, and then put the whole thing in again. This is going to be, this is f of t minus b1 squared plus g of t minus b2 squared plus h of t minus b3 squared. And now this is going to be less than epsilon. So that's just the distance. Whoops. Let's extend this further, like that. And now what we'll do here is we're going to square both sides. So if we square this, what we end up having is, then this will cancel. If we square this, this will cancel. We're going to get this over here, and we're all going to, yeah, this is squared. Yeah. So what we'll end up having is the square roots cancel. So if we just square this and then square this whole thing, etc. Yeah, so we'll just do that both sides. So what we get is this cancels. This will be like this: f of t minus b1 squared plus, like this, g of t minus b2 squared plus h of t minus b3, like this. And then this is squared. This is going to be now less than epsilon squared. All right, but each term on the left side of the above inequality is positive. So these are all positive because you have the square there, so it's always positive, positive, positive. So in other words, no single one of these is going to be greater than, no single one is going to be greater than epsilon squared, so because there is no negative ones. So in other words, every single one of these individually is going to be less than epsilon squared. So thus, what we're going to have is put these all together. So thus, if we have, and I'll put this starting from the beginning right here. So if this part right here, if 0 is t minus a, the interval is greater than 0 and less than epsilon, then here, and now we've essentially, we just squared these ones right here. So then what we'll do is I'll put this like this. The r vector function minus b, like this, and this is all squared. This is going to be less than epsilon squared. So that we get that, and we get every single one of these components. So we're going to get now this right here, f of, now let's fix this a bit better. This one right here, this is going to be f of t minus b1. Okay, because they're all positives, this can be less than epsilon squared. And then similarly, we're going to have g of t minus b2 squared is less than epsilon squared. And finally, we're going to have, this is going to be h now. H of t less than b3 squared. And I'll fix this up. Is less than epsilon squared. Here, I just shrunk those inside here, and and then we could just cancel all these squares though. So or we could just have f of t minus b1 is the absolute value because it's all positive there. So we just take the absolute value. It's less than epsilon. Yeah, so we just take square root of both sides and take the absolute value. This is going to be less than epsilon. We're going to have g of t minus b2 is less than epsilon. And finally, absolute value of this h of t minus b3 is less than epsilon. And these are just real valued functions, so these all have limits. Right, and by definition of real valued functions, we have, again, these are all just limits. In other words, if we have this scenario and then we have every one of these, then we just basically, the limit exists of each component. So thus, limit as t approaches, this is going to be a of f of t, this equals to b1. So that equals to b1. The next one is limit as t approaches a of g of t, this equals to b2, and then limit as t approaches a of h of t, this equals to b3. All right, and then by definition 1, by definition 1, this just means that we know that the limit as t approaches a of the vector function r of t, this equals to its components. Yes, in other words, this equals to, this is going to be like this, this right here, limit as t approaches a of f of t, and then limit as t approaches a of g of t, again just by the limit of the vector function is the limit of its components by definition, limit as t approaches a of h of t. Alright, so we have this. I think my calculus book uses actually a bigger bracket like that. But it's, yeah, I'll do the bigger brackets for now. Anyways, I've been doing the smaller ones before, but it's not a big deal. This is gonna now equal to, yeah, so this equals to, basically, this is gonna be, B1. Actually, I don't like these big brackets, I like the small one, it's pretty straightforward. I put bracket like that. Anyways, this is gonna equal to now, bracket B1, B2, because all these limits exist, B1, B2, B3. And this equals to, well, this equals to, I'll put it right, yeah, let's put it here. This equals to the B vector. So there it is. Or I'll put it like this. Limit t approaches a, yeah, of r of t equals to B vector. There it is. So we've proven the limit. So this is proving the limit from starting from the bottom of the definite or the bottom of the precise limit format. So we started. The first solution was you solve from. We were assumed this is true, and then we show that this is the case. And then the second one, solution 2, is we started off from here. We have this if and only if every epsilon and delta and so on. We get this, and then we show that going backwards is here. So yes, epic stuff there. All right, and now we'll go over here. The next part of that same exercise is visualizing the precise definition of a vector function limit. This is actually my own undertaking. This wasn't in the solution manual, but I thought it's pretty useful to do. So we can visualize the definition in 3D, definition, or just a precise, I'll just say precise definition of the limits in just the same way as we did in 2D. So if we recall from my earlier video, and here's screenshots from the calculus book. So basically, this is the visualizing the precise definition in real valued functions. This is in 2D. And then in the vector functions setup, we need to do that in 3D. Well, we're doing it in 3D and in vector form. So what this means is, and I'm going to do this actually half, I'm going to do this all like pretty much on the go right here. I haven't done this one. I did it before, but I think I did it a bit wrong. I'm going to draw X, Y right here. This is Y. So we're going to do this all improv right here. Yeah, that's the word I was looking for. Like here. So let's say we have this. All right, here I'm going to draw in red the vector. This is the vector B. So let's say we have vector B like this. This is B. And I'll put this right here. B vector. And this has components. B vector equals B1, B2, B3. And what I'll do is since it's already in red, I can just move this away. Okay, so it's going to look something like this. This is how it should be. And then I'm going to draw in, we'll draw it in black, the R vector. So this is going to be now, let's say we have an R vector that goes somewhere here. This is our R vector. Oh, this is our vector function, R of t. This equals to, yeah, let's put that, it's R vector. This equals to f of t. This is a vector function, g of t and h of t, like that. And now what I'm going to do is I'm going to draw a sphere. Let's say this was the farthest away at it was from this point. At this point is the farthest away that the R vector R vector function is from the B value. I'm going to draw this in blue. And what we end up having is a sphere. So we literally have a sphere where, and again, this is a parameter. So this is going to be right here. This is this parameter is between 0 and this is the absolute value of t minus a, like that. And this is going to be and it's going to be between epsilon, like that. So that's 0 is between t minus a. The absolute value is going to be between 0 and epsilon. And since it's a parameter, it's not going to be anywhere on the xy axis. It's its own variable that this that this vector function is dependent on. So then what we're going to do is so we have that point there, and also I'm going to draw the a value. So everything that's in this one here, the a is all the way across here. No, actually, that would be wrong. Okay, so the a is not there because again, a is part of the parameter t, but the center point is basically where the t value is. This is when t is equal to a. Yeah, so when t is equal to a, that's when we have it at this exact center point right here. All right, so that's what would be the t equals a there. I'll put it right here. This is at t equals a. So that is at t equals a, but again, that is, I'll just assume it's a, I'll just put a circle there. And then this is going to be at t equals a. Yeah, so that's the a there. All right, so that's the t equals a, but then this whole thing is in between it, and I'm going to draw this and highlight it now. Yes, I'm going to, actually, before we highlight it, yeah, so this is going to be like a sphere. Yeah, I'll draw it like highlighted. So the whole thing is highlighted in 3D. All right, here I just pause video and just highlight it, fixed it up. And I didn't highlight over this red just because it turns it into black. So anyways, we have that, like that. All right. Yeah, so if that's the epsilon, then the, if that's the delta, then the epsilon is going to be the distance between here and here. This is going to be epsilon like that. All right, and then finally what we'll end up having is, so I'm going to draw this in red now. So I move these over closer. So again, bear with me. This is going to put it down right here. So if we put this all the way down, all the way across here, we're going to get a now component. This is going to be, I'll put this as, this is going to be our B2. This is, B1, that's B1. And then this right here is going to be on all the way across here. This is B2. This is B2. And then likewise for the Y is going to, the vertical component has one as well. So the vertical component is going to be, yes, I'll just draw the vertical component. It's going to go across like this, dot, 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 dot. And this is going to be like that. This is going to be B3. And then, whereas this part right here at the bottom, I'll draw this in black. So this is going to be right here. This is the R. Just draw it around like that. So it's going to be somewhere around like this. So this is the R, and then it has the G, F, G, and H. But what I'm interested in is over here. So this distance right here, this is going to be our, we'll call this as epsilon 1. And then the Y is going to be all the way across here. This is epsilon 2. And then likewise, the bottom is going to be all the way across here. I'm going to draw this dot, 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 dot all the way across. And then the difference here is going to be, well, epsilon 3. So again, that's the component parts of it. So I just wanted to put that in there as a visual demonstration. Like that. Alright, so that is that. And I'm just going to keep it like that, otherwise it's going to get more and more messy. And now, and then as you shrink this interval between t minus a, as it gets closer and closer to a, this gets closer and closer, this gets 0, smaller and smaller. And then that interval, and this one gets closer and closer. So that's basically the limit as this is approaching closer and closer to this part right here. And I wanted to do this in 3D. Just basically you get a sphere-like setup there. This is the maximum value there. Yeah, this is the maximum. This is the epsilon is the maximum setup there. And between it, where this was the interval right here, and this would be the highest point, highest t value that gets this epsilon or gets close to it. But anyway, that's the maximum, and this number gets smaller and smaller, again, always greater than 0. Yeah, so this means that as we shrink, again, I just wrote it down, as we shrink the interval of the parameter t by picking a smaller delta right here, so yeah, as you get smaller and smaller towards there, because again, depending on the value of t, as it gets closer to a, but the main one is this interval right here, this parameter, this delta right here. So by picking a smaller delta, so if we can keep getting this super small, if there's always going to be a t value such that then yeah, such that the difference between here gets smaller and smaller if the limit then basically this is approaching that vector. then the difference between r and b gets smaller. In other words, epsilon gets smaller, and we can keep doing this indefinitely. In other words, the limit exists, and it becomes this vector. So all these approach these numbers right there. All right, epic stuff.